As a recap, this is the most important hydrological data that we have, the river flows, which we can get from a hydrologist, employing a hydrologist. So, a hydrologist will give us a table containing the average daily flows that we can expect from the at the diversion we have planned over the next 20-30 years. So, he has based his experience and these calculations on data as old as about 20-30 years. So, we can expect on average, for example, October 1st to be flow to be 2.7 or 2.8 cubic meters per second on average, but this may be different. For dry years it can be even 1, for wet years it can be 5, but this is the best average expectation that we can have based on the previous flow data or previous rainfall data. Therefore, so we depend upon this. But we can of course make couple of spot measurements on days, our own measurements, and confirm that they are in agreement with the general agreement with the actual flows. Or if you have a continuous flow monitoring system for a year, you can still get the things confirmed. And we now know that how to calculate these things and generate a flow duration curve. And in the flow duration curve, we will select a rated flow suitable for the economic conditions of the particular country or state we are doing the project. For example, here we might select 2 cubic meters per second as our rated flow and decide to go ahead with the project, because our economic calculation says that when 2 cubic meters per second is selected as rated flow, the economic parameters like internal rate of return are the best compared to other choices. So, we have done all these things. Now from why we invest in a hydropower project? To generate electricity. So, we want to make a business. So, we invest money and set up a, say for example, 2 megawatt small hydropower project. So, what we are going to sell are kilowatt hours or electricity units. Therefore, we have to make an estimation of how many units of electricity we can generate from this project if we select 2 cubic meters per second as our rated flow. So, we have to therefore make a calculation in order to determine how many units of electricity we can generate from the particular plant. So, that is what we are going to do today. This blue line columns here by your top like this I have colored top blue color columns are where we use the flow data to calculate or generate the flow duration curve. But today what we are going to do in this lecture, what we are going to do is this red color columns, right, which are marked in red color columns. How we can generate calculate the total generation of electricity from our project, right, and also top also I have put some summary information. Summary information I have put net head. Net head is something we have got it already, because we know the gross head, we know the head loss in the penstock, and after deducting it we have got the net head here. I have put it as a typical value 157. Rated flow I have put as 0.4. It does not matter whatever you can put, right, you can select. I have here selected 0.4, or rather we can say we can put 2, let us put it as 2, and then I have put a value here, efficiency of the generator and transformer as 94. Normally I told you that generators are about 96% efficient and the transformers are about 98% efficient. So, combined together 98% into 96%, about 94% is the total efficiency. And I have put also here something called minimum flow, right. So, minimum flow is something that environmental study will determine, and say river part where the water is we have diverted from it should have minimum environmental flow. So, I have put it as 30 liters per second or 0.03 cubic meters per second. Normally, it will be specified by the environmental authority who is giving the approval for the project. And this green color things here are to be calculated. This I have summarized here after calculations. So, that is what we are going to see. What should be our plant's capacity and how many electricity units, kilowatt hours or megawatt hours or gigawatt hours we can generate from the project, right. So, now I have put now our equation Q rho G H. Now, H is known, H is 157, net head is 157 that for project, and rho is 1000 cubic meters per kilograms per cubic meter, G is 9.81, we know that, and the efficiency and Q are the things that we want to know to calculate power. First, let us calculate power, then we will calculate energy, right. So, the power we have to know what is the efficiency at each flow rate and the flow rate at which the plant is operating, right. So, I have put a column here, right, put a column here as Q corresponding to our original line, right. So, here I have put here, see the value B 12 minus J 5, B 12 is the corresponding flow rate here 0.05 minus minimum flow, because at the diversion point we can divert, we cannot use full water coming in the river, we have to deduct the environmental flow, right, we have to deduct the environmental flow, right. That is the only quantity we can use in the power plant. So, if we use the flow available there, that is wrong. Therefore, I have here in the Q column, in this column I have put here the cell value is B 12 minus J 5, J 5 is the environmental flow here 0.03, that is why 0.05 becomes 0.02 here, right. Similarly, 0.01 becomes 0.07370 because we have deducted the environmental flow. Therefore, this Q is what is really available for the plant to generate electricity, right. Right, you get it, I hope you get the point, right. So, we have got the Q now, we want to get the Q for a given time and then we want to know the efficiency at that point, right, efficiency at that point, right. So, when the flow is 0.05, right, Q is this, then the efficiency of the turbine, how can we get the efficiency of the turbine? That we have to get from that curve that we discussed earlier. Suppose it is a, we looked at earlier efficiency curves with Q flow. So, if it is a Francis turbine, it will be something like this, right. So, we have to know our flow rate say 0.02, right, and then we can get the efficiency point, right. One way is to fit a curve for this efficiency curve. Efficiency curve, how do we get? Efficiency curve we can get from the turbine supplier. He will say this is the efficiency curve for my turbine, right. So, once you know the efficiency curve, theoretically you can fit a curve on this. I am sure that all the engineers are familiar with curve fitting techniques, right, using MATLAB or even using simple hand calculations, you can fit a curve on that parabolic or some curve suitable for this shape, right. Then you can just insert the flow value and calculate the efficiency. So, the efficiency will be a equation of flow, right. You can derive a equation for efficiency by fitting a curve here. Otherwise, if you cannot do that, you can just get the values manually, right. Manually you can get the values. So, maybe the efficiency may be 30%. So, I have put these values, I have calculated the efficiency at 0.05 to be 30% turbine efficiency, right. That how I have got it from a curve, right. So, you can manually get it if you want by looking at the curve and using measurements, or else you can fit a curve and get it. At 0.07 I have got as 52%, right. These are in percentages, right. And then at 0.15 70%, right, and so on. And you can see at 0.55 where the most number of days, 183 number of days, flow is in this range, right, in this range 183 days. So, efficiency is 89.2, right, 89.2. So, these things comes from the efficiency curve, right, efficiency curve. Now, once you know the efficiency, now you can calculate P, because other things are known already, right, other things are already known, these things are already known. For the Q, say Q is now for that particular date 0.05, efficiency is 30%, right. So, P is 0.3 into 0.05 into rho g h, all the values are known, right, these are the rho g h, right. So, once we do that, you can calculate this P turbine output, right, turbine output. So, turbine output will be here 9 kilowatts, right, at that particular, if you calculate it, you will find that turbine output is 9 kilowatt at that small flow rate, right. Similarly, when the flow is 0.1, 56 kilowatts. So, we can go on like that, right, go on like that. Right. Okay. So, we go on like that, but you can see the flow is becoming 1 here, right, flow is becoming 1 here, right, or rather we can say 1 here after deducting the environmental flow 1.02, we will virtually take it as 1, right. So, we have taken the rated flow in for this example as 1 cubic meters per second here, rated flow, right, that is from our economic calculation. So, once we do that, you can see at 1 point, at rated flow 1 no 1.02, almost 1 here, right. You can see now our rated flow is this, we are designing the plant for that. So, we can't have higher capacity than that, right, we cannot have higher capacity than that, because we have decided to have only 1 cubic meters per second as the rated flow. You can see if you look at the other below cells, plant capacity is going up and up and up, because the flow is increasing. We cannot allow that, right. Therefore, after this one, let us say 1000 kilowatt or 1 megawatt, we have to freeze the values, because plant does not, even though the flow is available, plant cannot generate, because the plant size is 1 megawatt, right. Therefore, we will freeze from here point onward, here the plant capacity here, sorry, P column, right, column P turbine capacity. So, here it is corresponding to 1 cubic meters per second flow is, sorry, I made a mistake earlier, it should be 1363, right, 1363 is the plant capacity corresponding to 1 cubic meters per second here, right, corresponding to 1 cubic meters per second flow rate, turbine capacity is 1363, right. We are looking at the here P turbine, right, P turbine. So, you can see now, so we cannot have beyond that. So, that is why I have frozen the value to, even though the flow is increasing 1.07, 1.12 etc., I have frozen it to 1363, beyond that. Flow increases, but we cannot have, because our plant is limited to 1 cubic meters per second flow rate. So, our flow rate is, rated flow is 1 cubic meters per second here, right. So, even though you have higher flows, your plant does not have a capacity to generate. You have limited the plant capacity corresponding to 1 cubic meters per second flow rate, right. That is why we freeze it here. So, at 1 cubic meters per second flow rate, plant capacity is 1363. So, even though the flow is increasing, our plant capacity will still remain at 1363, because you cannot generate anymore. Your plant does not have capacity. Your turbine, generator, all are sized to this 1 cubic meters per second rated flow, right. I hope you understand. That is why I have frozen it beyond that, right, beyond that. So, this is the turbine capacity column. I will this yellow column P turbine capacity, right. So, it increases as the flow rate increases, capacity increases 1050, 1118, 1186, 1254, 1322 and 1363, which is corresponding to 1 cubic meters per second flow rate. And when it comes to 1.070, our plant cannot use the extra water, right. 0.070 extra water it cannot use, because it has a capacity, penstock and everything. Your canal you design for 1 cubic meters per second, canal and the penstock everything designed for to carry 1 cubic meters per second. So, extra water you will allow at the diversion point to go in the river on rainy days, right. You get into your system only your rated maximum of your rated flow or below that, right. If it is more than that, extra water you let overflow into the river, right. So, together with the minimum flow plus extra water will go in the river, right. So, in dry day when the flow rate is less than 1 cubic meters per second, we have to send the minimum flow, but when the flow is more than 1 cubic meters per second, all the extra water will go in the river, right. All the extra water will go in the river, overflow and go in the river. But if you selected the different rated flow, if you selected say 2 cubic meters per second as rated flow, things are different. Let us see what happens then. In that case, if you select now, if you select 1 cubic meters per second, you have to freeze here, but otherwise you can go on generating. Say we will go until rated flow is 2 here 2.02. Let us see what happens there, right. You can see. So, if you select 2 cubic meters per second as your rated flow, your plant is 2753. We will assume 2.02 as virtually as 2, right. So, if you select 2.02, right, then you can generate up to that water rate, and then beyond that you have to freeze, right. Beyond that you have to freeze, right. So, you can see although the water rate has gone to 2.07, 2.12, 2.17, but still the capacity is only 2753, right, 2753, because your plant does not have capacity to generate with the extra water. Extra water cannot come in your canal. Canal is designed for 2 cubic meters per second, penstock is designed for 2 cubic meters per second, right. Therefore, you cannot generate more than that. So, you have to freeze it. Now, let us go back and say we finish it, we stick to 1 cubic meters per second flow rate, rated flow rate as we have assumed, right. Okay. So, you can see this is a turbine output energy power output test that at the turbine, that is the one that is input to the generator, input to the generator, and generator and to the rest of the electrical system, transformer and other things, right. Therefore, the plant output will be turbine output. So, this is the turbine output, power at the turbine, right, turbine shaft. So, the plant output will be efficiency of the generator plus transformer into turbine output, right, because after the turbine you have the generator and the step up transformer, for example, right. So, what is going out of the plant as the generation will be turbine output into efficiency of the generator into efficiency of the transformer, right. So, that is what we have got there as here. Now, we put a value here, generator and the transformer efficiency as 94% here, right. So, we multiply the turbine output, right, with 0.94, right, 0.94. So, this number has not changed because I think the decimal places you can see it is 8.7 really, because 9 into 0.94, right, 9 into 0.94, and the next one is 56 into 0.94, which is 53 kilowatts, right, plant output, 129 into 0.94, 122, right. So, this is the really the at the terminals of the transformer after stepping up the available power to be connected to the grid, right, available power to be connected to the grid, right. Okay. So, now we know the power, right, now we know the power what is coming out, right. Now, what we have to do is we are interested in calculating. So, if somebody asks you what is your plant capacity, now you can answer. If it is my plant is 1363. So, normally we will round it off, we will say 1400 kilowatt, right, because when you buy equipment you can't buy 1363, you can ask the turbine manufacturer I want 1400. So, we will come to the nearest 100 for practical reasons, but for calculations we can still use this. When you buy the equipment you will buy the nearest standard component, turbine or transformer, whatever, right. But we will for the calculation we will use the actual value as that 1363, right. So, you can see the plant output is when the it is running on full is this column I have to put little bit modify. Previously I have frozen it somewhere there. Right. So, when 1363 is the turbine output, plant output is 1363 into 0.94, which is 1281, right. I hope up to that point it is clear, right. Now, we are interested in calculating energy generation, right, energy generation. So, how to get the energy, right, how to get the energy. So, we know say on this particular day, say we will take this maximum number of days. There are 183 days, right, there are 183 days where the flow is 0.55, right, flow is 0.55 or the actual available flow after deducting the environmental flow is 0.52, right. So, the plant capacity is on that day 714 kilowatt, 714 kilowatt, right. So, there are 183 data days in this flow schedule, in this flow data sheet where the flow is in that range, right, 0.55 at 0.5 to 0.55 range. There are 183 days, largest number of days in the days that is in that range, right. Now, on that day when the flow is this much. So, in 183 days your plant capacity is 714 kilowatt, sorry 672 kilowatt, turbine capacity is 714, right, plant capacity is 672 kilowatt, right, in 183 days. So, we can do it now. So, 700 672 183, right, 672 183. So, you have 672 kilowatt, and for a day we are calculating, therefore, 24 hours, and there are 183 such days, right. During therefore, those 183 days, this much of energy will be generated, which will be 183 into 672 into 24 kilowatt hours, right, kilowatt hours, right. So, we multiply by 183 days. Okay. So, for that particular flow rate, this much of energy will be generated, and then if you go to the next flow rate 0.06, there are 27 days, right, 27 days. So, the plant capacity is flow rate is 0.57 actual flow rate after deducting the minimum flow, and then plant output is 738, right, 738, and number of days are 27, 738 into 27, 738 into 24 hours, this is kilowatt, this is hours, right. So, it becomes 27 into 738 into 24 kilowatt hours, this, right. So, this, then we can do this for all the days, all the flow rates, right, we can do it for all the flow rate, right, all the flow rate we can do for. But here you can see why I did not use these things, I have used it, but there are no days where the flow is this much, all are zeros, these are all zeros, right. So, even if you multiply with the plant capacity, the energy generation becomes 0, right. So, this number is really, right, this number is really what we calculated here, right, 183 into 672 into 24 kilowatt hours. I have divided by 1000 to make it megawatt hours there. So, this is in megawatt. I will put the units here. I will put the units here for your easy understanding. This is percentage, this is kilowatt, this is again kilowatt. Here I have divided by 1000, so that it is megawatt hours. Okay, right. So, this is in megawatt hours. You can easily divide this by 1000 and make it megawatt hours. This number is too large, that is why I have divided by 1000 to make it megawatt hours. This number is too big, so I have made it megawatt hours to make it, otherwise this will be 2.9 million something kilowatt hours, right. That is 2949 megawatt hours. Similarly, for all the other days, right, all the other days. So, we can calculate, and finally, at the end we can add up all these things. Here I have added all the generation kilowatt hours into, so it can generate 7531 megawatt hours, right, 7531 megawatt hours, right. So, I let you ask any questions rather than waiting till the end of the lecture. I would permit you to ask any questions, because it is important calculation, you should be clear. Any questions, or you want me to repeat it? Because from the plant what we can sell is kilowatt hours, the energy generation. So, we should be able to estimate that. So, this is how you do it. We have to do it day by day, right, day by day. Any questions from online or from physical present? So, it is not very difficult also, because it is just a please speak to the microphone.
So, this rho value is always 10 to the 3. Rho value
Rho is 1000.
Always it is 1000.
1000, yes, that is the density of water.
Oh, density of
It is
water.
the density of water, yes, right. Remember that we used it in the derivation of the equation P equals Q rho G H, E equals m G H, then the dE by dt is G H into m, and then we put the dm by dt as rho into Q, right, rho into Q. That is how the rho came. Rho is density of water. In that equation, rho is density of water, 1000 kilograms per cubic meter. So, it is a constant, right. So, rho and G both are constants. H will also be a constant once it is measured and gross head is measured and head loss is calculated and deducted, then you can get the net head.
So, irrespective of the water quality, it is a constant.
Yes, we assume so.
Okay.
Yeah, it will be very minor different, point maybe 999, 98 or 1002, 1003 if the water quality is bad, but it we assume 1000.
So, it is rounded to 1000.
So, yeah, it is a typical the density of water. Yeah, for all calculation it is good enough to assume as 1000. Any other questions? So, we can calculate energy generation in a similar manner, right. Maybe you can experiment on your own calculation and do this, right. And now we can use this for different other approaches. For example, now this is, now we are going to have a machine of say 1363, let us say it is a Francis machine, right, Francis machine. So, so now we told that earlier we can even put two machines, right. Say we decided here to put a one machine of 400 kilowatt, another machine of 1000 kilowatt, right, rounding off to 1400 plant capacity, right. In that case, how do we adjust this to reflect the new condition, right. So, so you can see that so then we have to we can get the efficiency curves of both turbines, small turbine and the bigger turbine. So, small turbine has a now a different rated flow, right. We have assumed here 1 cubic meters per second as our rated flow, right, rated flow. So, we can now divide it to corresponding to 1400 kilowatts. So, our when the rated flow is 1 cubic meter 7 cubic meters per second, our plant capacity is P is, let us assume 1400 kilowatt. We have rounded it 360 to 1400, right. And then now we want to have a 400 kilowatt machine and a 1000 kilowatt machine, right. So, we have to proportionately get the allocation of 1 cubic meters per second to the two machines. So, it will go to we want to divide it into 1000 kilowatt and 400 kilowatt. So, our flow rate for 400 kilowatt will be 400 divided by 1400, because our flow rate is 1 cubic meters per second, right. And for the bigger machine, 1000 kilowatt machine, so this will be the rated flow for 1000 machine, QR for 1000 kilowatt machine, this is the QR for 400 kilowatt machine. Right. So, let us calculate how much. Can anybody has a calculator, or we can use their phone and calculate. Or we can do it manually. Okay. .28. So, this will become 0.72, right, 0.72, right. Now, we get the efficiency curve of the small turbine first, right. So, now see how the flow rate increases, right, flow rate increases. Here you can see the flow rate goes on, right, until 0.27, right, 0.27 here, right. But there are no days where the flow is like that, right. So, we have to experiment it and see, right, whether it is worthwhile doing it, and then until then we can run the small machine, right, which will have a now here it says 350 kilowatt, 48 kilowatt, maybe theoretically you can say it is 400 kilowatt, right. And then generate first using the first turbine, right, first using the first turbine, and then afterwards start the second turbine if they have more water, right. I am sure that you can do these things with your own judgment, your own thinking, right, because it is a simple argument, right, it is a simple argument. So, you go on calculating power, right, until your flow rate is 0.28, here it is 0.27 is the one that is available here, right. So, all this will be generated by the small machine, right, but it is free, the efficiencies will be higher, this may be 0.5. Now, the efficiency curve for the small machine will have a higher efficiency values, right, higher efficiency value, because its rated flow is now less. I allow time for you to digest it, right, understand, think in your own terms, right. So, these values will be little bit increased because of the smaller machine, this may be 40, this may be 60, this may be 75, this may be 85, this may be 89, and all the others 89 until 0.27, where the first machine get fully loaded. So, it is capacity is say until 0.32 or whatever 0.27, 350 kilowatt, right, is the machine capacity, because we approximated to 1400, right, actually is now, but in the calculation it is shown as 0.27 and 350 or 348. Here we took it approximately, right. We have approximated to 1400 and 1000 machine and 400 machine, but in the calculation it comes as 348, because that approximation is not applying here, right. It does not matter for the calculation we use like that, but when you buy the equipment you have to use round values, right, 1400 kilowatt and so on. But now beyond that, now if there is more water still, now this we use when the flows are very low, right. And on the other days we can start to use the next machine, and then you have to go on calculating for that one separately, right. But now our selection does not seem to be very sensible here, because there are no days on which the flow is so low, right. All of them are very little. Therefore, maybe we can think of having two similar units if you want, right, rather than having 1401, we can have 700 into 2 probably. We can try that option also. 700 kilowatt into 2, right. So, that is an option, right. So, what we do is we do all these different combinations and look at the final energy generation, whether this number change by the new combination of machines, whether this total energy generation is increased or not. That is what is important to us. By putting two machines, we are trying to increase the generation. It should be substantially increased to justify the additional cost, right. To justify the additional cost, it must be substantially increased. So, we will prepare several sheets, worksheets for different combinations of the machines and see whether the total energy generation is increased or not, right, whether the total energy generation is increased or not. That is the intention, right, that is the intention. See whether you have any questions, you can digest it. What I am going to show you is this same sheet can be used for a variety of calculations, right, different combinations of the machines. Only thing is you have to sensibly put the efficiency values, so that you can get the advantage of higher efficiencies for small rated machines, right, small rated machines, small capacity machines. Now, 1400 kilowatt machine, kilowatt one machine, right, when the flow, that is 1400 kilowatt one machine with rated flow of 1 cubic meters per second. So, when it is 1 cubic meters per second, right, it will have maximum efficiency. But when it is when it is 0.5 cubic meters per second, efficiency may be 70%. Although we have selected 1 cubic meters per second as the rated flow, for example, 183 days flow is only 0.52 cubic meters per second, right. So, 183 days machine will operate somewhere here, right, with efficiency of efficiency of 70%, right. But now, instead of this you selected 700 into kilowatt into 2 machines, where Q rated for per machine is 0.5 cubic meters per second, right. Now, your machine has at 0.5 the maximum efficiency, right. Your this 700 kilowatt machine will have efficiency curve something like this, right. At 0.5 it will have 90%, right, at 0.5 it will have 90%, and at so you can see that then therefore, your machine will mostly operate at this point if you have the smaller machine. 183 days your flow is 0.5, right. Therefore, your machine will operate here, at a peak efficiency point, because you have opted to have a 700 kilowatt machine. So, that is the advantage of changing the machine capacities and seeing how we can use the efficiency to our advantage, right. Therefore, in your calculation, here, so you will go until here you can see 700 kilowatt, right. Let us say approximate 672 here, this one is the corresponding one. So, you will go on with here, but you can see then your now this efficiency curve values, now we have to readjust, right. These values you have to readjust as per the new curve of the 700 kilowatt machine, which will be much higher numbers for these part loads now, right, much higher numbers for the part loads. Here you can see earlier they were for the part loads, they were smaller earlier. If you take at this one, earlier it was smaller because of the previous curve, but as per the new curve it is a high efficiency point, right. Therefore, this efficiency values figures we have to readjust, these efficiency values we have to readjust to suit the new curve that corresponding to the 700 kilowatt machine. So, that will increase the amount of energy generation, right, because of the high efficiency of the turbine. And then we will look at the total generation, how much it is increased, right, how much it is increased. I can take any questions if you have. Of course, you know that you can have your own other methods also for this kind of calculations, right, all the other methods, but you can you get the when you get the idea, you can develop your own method, right. You can develop your own method, you do not have to go by exactly the way I have prepared the Excel sheet, but you get the common sense. What we want is every day when we get the flow duration, this flow data, from flow data how to generate electricity, because we know October 1st flow is this much, then we can apply our equation P equals efficiency into Q rho G H, this is Q, right. So, you can calculate for that day, right. If you want, you can do separately for every day, right, calculate the power and the energy, right, but on there, but it will be going up and down like the time series that we talked about earlier, right. So, if you just plot these 365 points in a time series, how will it look like? You can put all these things to a single column and plot a time series. So, it will be varying like this, right, Q, this is Q, right, and you can calculate P also, plot P also, P is equal to efficiency into Q rho G H, these things are constant, efficiency value you can get corresponding to the Q value, Q is here, this is number of days, right, 365, day 1 to 365, right. So, you know the Q value. So, you plot the P, right, P will be also going in the same way almost, right. So, this will be the power generation, right, this will be the power generation. Then power into, you can every day you can calculate power into 24 hours, right. Every day you can calculate the power value, power into 24 is the kilowatt hours, right. So, it is but it is not easy to calculate, you can see it is a analog curve here, That is why we did it in a different way here. But if anybody is interested, they can do this way also. They can put all these values in a single column, 365 days. For each day you can calculate how much power, how much energy, and then add it up, right. So, that is all, that will also give the same answer, right, same answer, but for each flow you will have to get the corresponding efficiency from the efficiency curve, right. For October 1st, efficiency corresponding to flow of 2.7, October 10th, efficiency corresponding to 7.7, and so on, right. So, that is a little bit cumbersome because the data points are random, right. Random means continuously changing. That is why we put them into class intervals and organize them and then did this calculation, right. But that in the row way also you can do, right. For each day you know the average flow. Once the flow is known, power you know, P equals efficiency into Q rho G H, and then 24 hours kilowatt hours, power into 24 kilowatt hours, right. That is also a method of calculation, right, method of calculation. Finally, it should be the same. If you use the same efficiency curve, same efficiencies for transformers and generators, etc., both calculations will give the same answer. But we did it this way because we can generate the flow duration curve and determine rated flow. All these things are easier this way. Otherwise, by looking at this data set, we can't decide the rated flow. No scientific way of doing it.